This video will reintroduce some of the topics, some of the calculations and units for electricity that we've done, and then go over Ohm's Law Lab, what you hopefully found, and at least get everybody on the same page with Ohm's Law, which is the most important electrical formula that there is. And it's applicable to everything around us that's plugged in or has a battery, all the little components, all of it. So to start, let's review the three important characteristics that we can measure pretty easily. First one is voltage. All right. Voltage, remember, we abbreviate with a V, and we measure in volts. So there's lots of V's with this. We abbreviate volts with a capital V. Can be a little confusing, but depending on the context, we know which one we're talking about. Usually we just say volts. This is the energy pushing electrons through a current, through a circuit. We often refer to it as either a voltage difference or a voltage drop. Those all mean the same thing. The difference is usually used when describing a battery, but could be on two sides of a component like a resistor or a light bulb or a toaster or anything. It's just a difference in energy from one point to the next. And same with drop. That describes how much voltage, how much energy is being lost by electrons going from point A to point B. All of those mean the same thing. Whenever you see any of them, we're talking about voltage. There's no, although they go by different, slightly different names, they all mean the same thing. Second one is current, which for reasons that I haven't found is abbreviated with a capital I, and it's measured in amps. Sometimes we lengthen that to amperes, which is the Americanized version of the scientist's name, Ampere, but amps is the most common, and we abbreviate that with a capital A. These are capitals because they are named after people. This is how much or how many electrons flow past a point. It's not a strict counting of them. They are uncountable. They're just so many, but it's a measure of that, the amount of charge. And then third one is resistance. We label that with a capital R, and we measure it in ohms. And the symbol for ohms, we can't use an O because it looks too much like a zero. Oh, I just got this note. My assistant looked it up. It comes from the French, and that's going to be a struggle to pronounce. Intensité de courant, so intensity of current. There isn't. We do use both capital and lowercase c in other places, and maybe we did that before this intensité was named, and so we didn't want to use the exact same thing as in others. Okay, back to resistance, which uses, instead of an O for ohms, which would be confusing because it looks like a zero, we use the Greek letter omega. Ooh, that's an ugly looking omega. The last letter of the Greek alphabet, and this is a capital version of it. And so we do it that way. Now, when you're doing homework or typing anything, it's easiest just to type it out in ohms. I have the Schoology quizzes set to allow you to do that. You could find this symbol, the omega symbol, and paste it in, or if you have a keyboard like mine with this numeric keypad part, there is a code that will actually put it in directly, but it's not really worth learning at this point. Just type it out, OHMS, preferably with a capital O, because it is named after a person, Georg Ohm, a German scientist. This is a measure of the what's the resistance to flow. So how hard is it for electrons to flow through a thing? Okay, so those are our three main measurements that we make in electricity. The last lab, titled Ohm's Law, after this Ohm's person, one of his big contributions, asked you to take some data by changing the amount of voltage in the circuit and then measuring the current. Voltage is controlled pretty easily by changing the battery. But when this is plotted and as part of the instructions, I actually ask you to change it up, and instead, when you plot it, plot voltage as the dependent variable and current as the independent variable. So that would mean current should go down here. Voltage along this side. And then when you plot that and then add a best fit, find that right away that it is a line. It doesn't have to be any particular slope. And you got a formula for this line. We'd write it often y equals mx plus b. But in this case, if we think about it logically, although our measurement might have been a slight bit off, and so our best fit curve might have a value of b here, if we look back, if we don't have any voltage, we won't have any current either. So this actually should cross, using this as our model, right at the 0, which means we can actually ignore that b. Our data might show a little bit different, but when we're looking at a bigger picture, we can ignore that. And then we wanted to put in values from our graph rather than y and m and x, which have generic meaning in math, but not really meaning in this context. So our y here was our voltage. So instead of y, I'm going to write the symbol for voltage, capital V. Our x variable down below was the current. And remember, current is abbreviated as capital I. And then we had some number. I'm just going to put a number in here, 10. Let's say it was 10. Well, that number should have been important in your lab. In fact, that number is your resistance. So we could even rewrite this more generally as V equals R times I. That is Ohm's law right there. Georg Ohm was apparently the first person to recognize this relationship. So scientists later on named it after him. Now, sometimes this is written in different order. It always means the exact same thing. This is what we're going to be practicing using during our calculations for this portion, for this homework 5.1. So I'm going to come down here and we're going to do a couple examples and see how can we apply that to various situations. So here's my first example. It asks how much voltage is required to push 2.5 amps of current through a 150 ohm electrical appliance. So going through, as usual, read through the questions. This whole quarter, you're only going to get this one equation, so we can be assured that we're going to be using it for these calculations, and I'm just going to rewrite it here. We can either write it V equals R times I, or V equals I times R, since it doesn't, the order doesn't matter. The second way is the more common way to see it. but it doesn't make any difference. Our 2.5 amps, well, amps, I remember, was a measure of current, or intensité de courant. So I'm going to label this with my I for current. 150 ohms, well, that's a measure of resistance. I'm going to label that with my R. And I see down from my formulas down here, all I have to do is multiply those two together. So 2.5 amps times 150 ohms. And since I'm writing it with a pen, I can just make that symbol, not very well, but well enough. Multiplying those together gives me 375 volts. When I multiply them together and get voltage, I am looking at volts. Pretty easy. Okay, on to our next question. Just check. Good. Question 2, example 2. A standard incandescent bulb, this is the one with the filaments in it, that is connected to a 120 volt circuit in our homes, has a 0.5 amps of current passing through it while it's lit. What is its resistance? So this is the standard screw-in bulb that you have in lamps and light fixtures. We're switching more over to LEDs, which is saving a ton of energy, but this has been a standard for a long, long time, and you probably still have some in your home. So in this case, we've got 120 volts up here. Okay, well, that's clearly a voltage. 0.5 amps of current. Current is abbreviated with I. I know from Ohm's law that V equals I times R, but this one's asking me what is its resistance. So that means I have to rearrange this formula and find what is R equal to. So it's I times R there. I have to do the opposite. So I'm going to divide by I, and I have to do it on both sides because those are the rules of algebra. In order to keep the two sides equal, I have to do that. So on the left-hand side, I have V divided by I. On the right-hand side, though, I and I cancel, so I'm just left with R. And I can put my values in this way. So R is equal to 120 volts divided by 0.5 amps, and that is 240 ohms. Now, I'd probably write it that way, but if I were answering it in as a with the Schoology quiz, I would write it as 240 ohms with a space in between there. Don't forget that space. Schoology is not smart enough to understand. So when we were up here with our previous example too, this 375 volts is fine. Just make sure you've got a space in between them. Okay, and one other thing, there are only 3 things I can ask you about with any of these questions: V, I, and R. I've already asked you about V and I, and R, I should say, so you can probably predict where we're going. How much current flows through a 5 ohm toaster wire that's connected to a 120 volt wall outlet? Toasters are pretty simple devices. At the simplest, they have this wire that heats up as electricity passes through it. All wires do, and works like a light bulb. And then it's got a timer of some kind. So this toaster has a 5 ohm wire. Well, ohms, that's a measure of resistance, connected to a 120 volt wall outlet. So that is obviously V because it's volts. And I want to find what is the current, how much current. Okay, so I start with my V equals I times R, Ohm's law. I want to solve for current this time, which is the I. So I got to get rid of that R. Since it's I times R, I have to divide both sides by R. These cancel, leaving just I on the right-hand side and V divided by R on the left. So I take my 120 volts, divide it by my 5 ohms. Don't want 24, I think, but don't want to make a silly error. 24, and then the units for current are amps. Again, don't forget that space in between them, but otherwise the calculation's really just that simple, and they're only the three that I can ask you about. So although this seems really simple as we're going through it, and mathematically it is, this is really powerful because this tells you a lot about the electricity use in your house. Everything that we use electrically is governed by this. Okay. Hope this helps, and good luck.